the bond. Hydrogen uses s orbitals. S orbitals are spheres, as shown here. So this is a picture. This is supposed to be a ball. I'm just drawing a circle. And I'm giving you the sign of the wave function, the s orbital, and this is purely mathematical mumbo-jumbo, if you wish. It can be either plus or minus. But when one orbital interacts with the other, if the two signs of the wave function are the same, this will be a positive overlap, a so-called in-phase overlap. And this makes a more stable molecular orbital where all the electrons, or the charge, if you wish, is delocalized around the hydrogen. So, or if you were to put an electron in here, you would find that electron in a big donut around the two hydrogen atoms. So this in-phase overlap, remember this is the sign of the wave function, plus and minus, not charges, is called bonding. Okay? In the scheme that is the mathematical scheme that is used to describe bonding, you interact in phase and out of phase. Okay? So the in phase gives you the bonding orbital. The out of phase means that you're interacting a plus with a minus. So as these guys start overlapping, plus subtracts from minus such that there is nothing in between the two hydrogens, and there is a change of the sign of the wave function. That's called an anti-bonding orbital, which is of no significance beyond this mathematical construct until you start putting electrons into H2 to, for example, make H2 minus. Then an electron, since the bonding orbital is filled, will have to go into the anti-bonding orbital. And this is why H2 2 minus, with 2 electrons in the anti-bonding level, is unstable. It falls apart into 2 H minuses because there is as much anti-bonding electron density as bonding. In an energy diagram, you just generate a level for the s orbital. Artificially, I've just drawn it here with this line. And here's another s orbital. And this mathematical mixing in phase and out of phase means that you get 2 new levels, 2 new molecular orbitals. One goes up and one goes down. And the essence is that since you only have 2 electrons, the 2 electrons go into the lower orbital. And this is the reason why the normal bond only involves 2 orbitals, 2 electrons rather. It's an electron pair and not more, right? In all of the chemistry we've seen, the normal CC, CH, CBr bond, it's 2 electrons. Why? Because 2 orbitals, and with other cases, there can be hybrid orbitals and the like, but it's always 2 levels interacting. They may not even be at the same energy. One goes up, one goes down. And because there's only 2 electrons to then fill up this new molecular orbital picture, they always go down there into the bonding level. That's the molecular orbital rationale for the stability of the 2 electron bond. So what happens when you do this to ethylene? You construct ethylene by looking at the 2 bonds separately. So there's the sigma bond, which is indicated here, where we look at the sp2 hybrid on the left and another sp2 hybrid here. So here the 2 sp2 hybrid energies, and you do the interaction. One goes up, one goes down. And here are the 2 electrons that make up this bond here. There they are. Okay. Separate from that is the pi bond. Now the pi bond, you do exactly the same, but now you're just focusing on the energies of the p orbital. So here's the energy of this p orbital, this p orbital. One goes up, one goes down. Now the difference between the sigma bond and the pi bond is because the overlap is weaker for the pi bond, the energy splitting is less. So the electron pair that's moving down into the bonding molecular orbital moves down less than the electron pair that moves down in the sigma frame. Okay? It's another way of saying the pi bond is weaker than the sigma bond because the stabilization by that interaction is not as good. So we're taking this and putting that into the energy diagram. Here they are, these 2 levels. The sigma levels are the antibonding has gone up higher than the pi star, than the antibonding pi, and the bonding has gone lower. So I'm just dumping both bonds. They're two separate bonds. I'm just putting them into the same energy diagram so you can relate one to the other. But we'll look when we look at the allylic system exclusively at the pi system. So starting with ethylene, we have the pi bond, the bonding molecular orbital, and the anti-bonding molecular orbital, these two. And now what we're going to do is interact these two orbitals with a new p orbital, which makes up the allylic system. And there's text that I will now describe in my words, so you can read up on this later. But here's the diagram. It looks a little busy, but it's actually simpler than you think. On the left, we start with ethene, okay? The bonding pi, the anti-bonding pi orbital. And on the right, we have the p orbital, okay? The p orbital we put in the middle. It's at the 0 level. The p orbital is defined as, this is an artificially defined 0 level, because the p orbital is not undergoing any bonding. So we'll call that 0. Okay? But this is artificial. You can take away the number. Okay? It's in between these two, in fact, smack in the middle. And we're interacting this orbital with these two now. Okay? So if you do the stepwise, interacting this orbital with this molecular orbital means a splitting. The p orbital will go up. The pi orbital will go down. But we also have, at the same time, we have to interact this p orbital with the pi star. This means that the pi star will go up and the p will go down. So interaction with this will push p up. With that, we'll push it back down. Since the p is right in the middle, it gets pushed up as much as it gets pushed down, i.e., it stays where it is. It doesn't move. It just moves here. So what? Where's the stabilization? Well, the stabilization is because these two electrons get pushed down. Okay? So that's where the allylic stabilization comes from, regardless of whether you have an electron in the p orbital, as in the allylic radical, or you have no electron there, which would be allylic cation, or you have two electrons, which is the allylic anion. This guy always goes down relative to the single pi bond. And that's where the stabilization arises. Okay? And so the new energy picture is you have a filled 2-electron p orbital. There's the pi molecular orbital. Here's the p orbital. And depending on whether you have plus, dot, or minus, you put in electrons here or not. And the resulting nodal picture is the lowest energy orbital has no nodes. The next orbital takes a node. This is just the same as we've done with s, 2s orbital, the p orbitals, and higher orbitals in the Aufbau principle, back to chapter 1 if you don't remember that. So this one has a node. The node, for symmetry reason, goes straight through the center carbon. And the electron density, or charge, is located exclusively at the termini of the allylic system. Something that comes out automatically out of the resonance picture. Remember, when we drew the allylic resonance, the double bond moving from one side to the other, and therefore charge or dot moving to the other side, the action part was always at the termini. This is the molecular orbital picture that makes you understand that in quantum mechanical type terms. Okay? So if you got totally lost here, that's okay. Forget it. Let's now look at something that I do like you to take home, and that is the allylic, the reactivity of the allylic position. And I think that's a good place to have a short break. So here's now something I want you to take home, and that is actual chemistry. So how does this special stability translate into reactivity? And the first one is allylic radical halogenation. A very surprising experiment here. You take propene with bromine with a twist. It's not the normal bromine at high concentration, 1-to-1 mixture, but very low concentration. concentration that is so low that the normal bimolecular, which is highly concentration dependent, of course, step of electrophilic addition to the double bond slows down. Gets slower and slower and slower. Another reaction takes over, and that's a radical halogenation reaction, which is completely analogous to Chapter 3, the radical halogenation of alkanes, saturated alkanes, facilitated by the special lability of the allylic CH bond. If you do this on the low concentration, the double bond reacts too slowly by electrophilic addition. Instead, it gives bromine a chance to dissociate in the presence of light or radical initiators or just heat to make Br dot. And that Br dot sets in motion a radical halogenation mechanism, which generates the allylic halide, the allylic bromide product, plus HBr. Okay? So this is another mode of reactivity of bromine with alkenes. If you do this under high dilution conditions, or as we shall see, even better with a special reagent called NBS, then you get allylic bromination. What's the mechanism? That's old stuff. It's identical. So you're not learning anything new here. It's the same as the alkane halogenation. Dissociation to bromine dots. Then, and this is the initiation step, this is the guy that starts a propagation cycle, namely propene plus bromine dot. The CH bond gets broken. You make HBr and the allylic radical. And the allylic radical has resonance, so the two resonance forms, and shown here again. And then the radical reacts with bromine and gets you to the corresponding bromide product. There are termination steps. Termination steps in any radical mechanism are loser steps. You want to avoid them. They don't happen very often because the radicals floating around in solution are there in minute concentrations. All you see is mainly starting material and then product building up. Everything else happens in between with minuscule concentrations of these reactive species. If they find each other, it's death. It's death to the propagation cycle because you need the dots to propagate the cycle that we just saw a minute ago. So this can be any radical recombination to make any of these species, or in fact any dirt in the reaction mixture on the walls or whatever can, in principle, cause your reaction to stop. So typically, radical halogenation experiments are run with continuous radiation using external light to make sure there's always a certain amount of X dot, in this case Br dot, present, or you add a radical initiator like a peroxide or something like that that ensures that there's a radical presence. A much more convenient reagent for these radical halogenations is actually this beast here called N-bromosuccinimide, or IUPAC calls this N-bromobutanimide. We'll come back to nomenclature of these kinds of species when we talk about carboxylic acid derivatives. But the crucial part is it's got this NBr bond. And this guy, when exposed to traces of HBr, which are always present in the starting NBS, decomposes in solution to generate the NH species and Br2. So this Br and that Br combine to make Br2 and this species here. But it serves by this mechanism as a time release Br2 generator. So you're leaching into your solution slowly Br2, which is exactly the high dilution, low concentration conditions you require to have Br2 at low enough concentration that the electrophilic addition to the double bond is too slow. And the radical mechanism has a chance to take over. What's the mechanism of this step? I'm giving it to you because a lot of people always ask for it. But this is not something I'll test for at this stage because this is really later chemistry. But what happens is the carbonyl oxygen gets protonated by the HBr to make this protonated species for which you can write two resonance forms. And notice in this color scheme, green groups are leaving groups, electrophiles are blue, nucleophiles are red, green is the leaving group. It becomes a leaving group because this species, stabilized by resonance, is attacked by Br minus on the Br to generate Br2.